surfaces and surface area is one of the lesser important topics this semester, so I'm going to do this one kind of quickly and not go through all the details. The derivations are very long and not as insightful as in some sections. I'll just point out one additional thing in addition to this section that is kind of important is surfaces of revolution. There's this formula in them. If you have a surface whose radius at each point x along the x-axis is f of x, and it's a continuously differentiable function, you can take the surface area of that surface obtained by revolving f of x around the x-axis between x equals a and x equals b and get this formula. You had this before. Integral 2 pi radius times square root 1 plus radius prime squared. So keep that in mind, and now we're going to do the more general case. Suppose we just have a surface area over a plane region. How do we find the surface area of that plane region? Well, we can think of breaking this little plane region up into little rectangular subregions and take the area over each little rectangle down in the plane and add up the areas of the little rectangles above, and that would approximate the area of the surface, and take the limit as the number of little, they're actually parallelograms over the rectangles. You have a rectangle down here, and over the top sits a parallelogram tangent to the surface. When you add up all those parallelogram areas, taking the limit of the sum, you actually get a nice formula. Here's the derivation that they have on the next page. I just want you to have an idea where it comes from without going through all the details this time. Let's see. Yeah. The area is actually equal to the cross product. There it is, way up at the top. It's hard to read, this thing is so small. But the area of the kth parallelogram up over the, up tangent to the surface, delta sk, is approximately so the surface area, delta sk, is approximately the area of the parallelogram tk, which you can show without too much difficulty that that's the cross product of the vectors along the edge, qk and rk, are the vectors along the edge of the parallelogram. Remember, the area of a parallelogram is the length of the cross product. That's what this is saying. And so you add up these kinds of things. Well, these are the tangents, qk and rk, to the surface. They turn out to have these vectors. And when you take their cross product, you get this vector. And then you just need its length. And so when you take the length of the vector to get the area of the kth parallelogram tangent to the surface, you have this. And then when you take the limit of the sum of all these, the length of this is root sum square of the components. This squared plus 1. That's where this crazy formula comes from. When you take the limit of the sum of those, we'll define that to be the surface area. So the surface area will be the limit of the sum. We'll say this is approximately this, and you take the limit of the sum of this, and you get the exact surface area. You can show that the errors have to go away as you get more and more little rectangles in the plane with the limit of the y-swing going to 0 in both directions. Well, what is this? This, by definition of the definite integral, is actually equal to this double integral over the plane region down in the plane over which you're looking at the surface. So to evaluate, that shows that to evaluate the limit of the sum of the little parallelograms, you just have to evaluate this double integral. So that's the first formula, and actually the more important one for us, I think this is the one people usually use in practice. Suppose you want to find the surface area over a region R in the plane of a function z equals f of xy. This is the formula that we just did sort of a hand-waving proof of. And here's a nice example that they have in the book. Let me see if I can blow this up so you can see it. And we'll just illustrate it by example. I just want you to be able to do the same thing for a few homework problems. This is not intended to be a long complicated section. It's not got as many applications as some sections. Suppose we wanted to be over the right circular cone, x squared plus z squared equals 4, right? Right in the plane, in the xz plane, this would be the circle of radius 2 at the origin. And so when you leave y out, then y is arbitrary. And so this is the circle is extruded around the y-axis of radius 2 to make a long, let's say, cone cylinder, to make a cylinder of radius 2. So the surface area of this cylinder, if I want to take the portion of the right circular cylinder, whose coordinates satisfy x is between 0 and 1, and some of it's cut off here, and y is between 0 and 4. Suppose I want to find the area of that cylinder. So here's what we have. Maybe I should draw the picture just to show you. The cylinder looks like this. Here's the portion of it that's over x between 0, oops, that would be 0 to 2, wouldn't it? 0 to 1 would be this part of it, and between y equals 0 and y equals 4. Let's put it back this way. So between y equals 0 and y equals 4 and x equals 0 and x equals 1, it's over this rectangle in the xy plane. We want to find what is this surface area right up here. S, if you like. So we just have to take z equals square root 4 minus x squared. We solve on the cylinder. X squared plus z squared equals 4 for z. So this is the equation of the surface. Z is a function of x and y. And in this case, it depends only on x. And we have to calculate the double integral according to that formula. The square root of dz dx squared plus dz dy squared plus 1 dA. And it looks crazy, but again, you can see where it came from and say, oh yeah, that makes sense. So dz dx, taking z equals square root 4 minus x squared, is minus x over square root 4 minus x squared just by the chain rule. That needs to be squared plus dz dy. Well, z doesn't depend on y, so its partial derivative is 0, gets squared, plus 1 dA. If we can evaluate this integral, we can get the surface area. One of the reasons this isn't really useful is that in practice, usually you get a square root that's too hard to do, and you just can't do it. So in this case, actually, however we can, this is x squared over 4 squared minus x squared, plus, this is 4 minus x squared over 4 minus x squared if you give them the same denominator. And the x squared here, and the 4 minus x squared, the x squared cancel, you wind up with 4 over 4 squared minus x squared in the square root, and it reduces algebraically to this. So going from here to here is just algebra is the point. Square root of 4 on top and square root of 4 minus x squared on the bottom. And now what's this one? We remember our formulas before. You make a u substitution. 2u equals x, and this becomes 4 minus 4u squared, and it comes out to be an arc sine. So with your calculus 2 integration stuff, you can find out that this is actually the arc sine, the inside integral with respect to x. Plug in 0 and 1 and take the difference, gives you pi over 6. Then we have to integrate with respect to y on the outside, wind up with 4/3 pi. So that's all there is to it. It really helps you to sketch the surface and sketch the plane region below. That was the key here in this problem, was you sketch the surface. It's a cylinder. You can draw the rest of it around like this if you want. You sketch the plane region R over which you want the surface area, and then you integrate over the plane region that big square root that we saw. I have trouble remembering this all the time. Maybe this will help you remember it. This is an analogy actually to what you did in Calculus 1, where you had an arc length from A to B, and a function y equals f of x that had a continuous derivative. You can find the arc length of this how? You said the arc length is the integral from a to b of the square root 1 plus f prime of x. Let's write it this way, df dx, you know, write it this way, df dx squared plus 1. It's often written in the other order, but that's what you got by taking a bunch of little secant lines and adding up their lengths and taking the limit as the number of little secant lines went to 0 to get the arc length. Remember this one? Similarly, over here we get a very similar integral, adding up a bunch of little tangent parallelograms over a rectangle down here. Here we just incremented this. And when you add these up, we get the surface area is a double integral, since it's over a plane region instead of over a line segment. So we double integrate, and the square root just has one more term. It has the df dx, now it has a partial derivative squared, plus 1, and dA since it's over a plane region, and just one more term, df dy squared. So here's how I found out I could memorize this formula. It's just like what we did for arc length with one more term, and you have to write partial derivatives and double integral. So it's a very similar concept to do this, and maybe this doesn't seem so awkward anymore, hopefully. All right. Well, the next part I'm going to mention is not as useful in industry and other applications, but you want to have seen it. It pertains to some of the theory that you get later. There's a second way to do surface areas, and that is to think of them as the surface as a parametric surface, and that comes up in lots of applications too. So let's see if I can get this up here. Suppose, again, you have a surface, but this time you're thinking of a region in UV space, and you're taking x and y as functions of u and v, and so corresponding to a plane region in UV space, you get a surface in, a plane region in x, y space, and take z is a function of x and y that in turn are functions of u and v. So z is a function like this. How can we now find the surface area? By the way, I guess I should mention here that this allows more general surfaces too. More generally, instead of writing x and y as functions of u and v, and z as functions of x and y that are in turn functions of u and v, you can just write all three of these as functions of u and v and generate a surface that way also. So that's what this write-up has done here. And now what you can do is say, well, if I hold v fixed and let u vary, then I get a curve like this, a constant u curve. Right? If you just have a function of one parameter, one real number, what you get in typically is a curve in 3 space, right? Now if you hold u fixed and let v vary, then these things become a one parameter description, and you sweep out a curve. And so what you're doing when you hold one of these fixed is sweeping out a curve and sweeping out a curve, and you realize now, if I were to hold one of them fixed, I could take the partial derivative with respect to the one that's not fixed and get a tangent to this curve. I could do the same the other way and get a tangent to this curve. And the two tangents, I can take their cross product and get a normal to the curve. And then I have a normal tangent plane there because I can figure out what the normal vector is. So these kind of things all come into play. And now, jumping ahead a little bit here because this is quite complicated and not real illustrative, I'm just going to say, but what I've mentioned here is that you can get a normal vector to the surface by taking dr du cross dr dv, where r is the position vector, right, moving around on the terminal point of which moves around on the surface. So dr du is a tangent vector to the one curve that we showed. Maybe I can get this on here. Dr dv is a tangent to the other curve. Here they are. Dr du, dr dv, that's what I was motioning my hands and you couldn't tell what I was imagining with this. And their cross product is a normal to the surface. So here's the given parametric equations, x, y, and z as a function of u and v, how you then get a normal to the surface. Now if you divide it by its length, you have a unit vector, so that means that when you want to find a unit normal to a surface, you can use this formula. If the surface is given parametrically, dr du cross dr dv over the length thereof gives you a unit normal to the surface, if I like to use sigma for it. So there's the next application, is finding a unit normal to a surface. Well, if you can find a unit normal to the surface, then you can find a tangent plane, right? You can, let's see. You can just take that normal vector and take the point at which is supposed to be tangent, and between the point and the normal, just write down immediately the point normal form. Let me do one problem out of here. This pertains to your homework. It says this. Suppose that r is equal to u cosine vi plus u sine vj plus vk. Suppose this is, sorry I've been drawing on this other page and not showing it to you. Oops. I just didn't get it up there. There we go. Suppose this is sweeping on a parametric surface. I don't even know what it looks like maybe. And I want to find a tangent vector. Find a tangent. And then a tangent plane, maybe at the point 1/2 pi over 4. What can I do? I first find a normal vector by simply finding dr du. Alright, well I just take partial derivatives here and I get the vector cosine v, sine v, 0. I take dr dv, and I get minus u sine v, u cosine v, and 1. And then I take their cross product. So dr du cross dr dv. Alright, we just take, for the first component, this times this, 2 times 3 minus 3 times 2, this is the fast way to do it, is sine v. This times this minus, minus this times this. And then 3, 1 minus 1, 3 for the second component is 0 minus cosine v. And then 1, 2 is u cosine squared minus 2, 1 becomes plus u sine squared. So the third component is u cosine squared plus u sine squared is just u. And so there's their cross product, done very quickly. Dr du cross dr dv. And now this, however, is a normal vector. I could call that n or something. Is perpendicular to the surface. Now if I want to find at the point a tangent plane, I simply say r of 1/2 pi over 4, plugging it into the original function up here, becomes 1/2 cosine pi over 4 is, cosine pi over 4 is 1 over square root 2. So 1/2 times 1 over square root 2 is 1 over 2 square root 2. Just by plugging in u equals 1/2 and v equals pi over 4. Then similarly, u equals 1/2 and v equals pi over 4 gives 1/2 times sine pi over 4 is 1 over 2 square root 2 also. And then v equals pi over 4. This is the vector to the point on the surface. And for the tangent plane, what I need to do is just say, well, this end of this vector here is also the point on the surface, so this is a point on the surface, x0, y0, z0. And then I have a normal vector, it's this one, a, b, and c, are these three numbers, and I better put them in at the point. Also the normal vector at the point, 1/2 pi over 4, has component sine v, which is 1 over square root 2, minus cosine v is minus 1 over square root 2, and u is 1/2. And so this is your ABC of the tangent plane. And now you say the tangent plane is simply, by the point normal form, a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. When you're given a point and a normal, you just plug the numbers in and you get this. What we have then is 1 over 2 square root 2 times x minus 1 over square root 2 plus minus 1 over square root 2 square root 2 times y minus a minus 1 over square root 2 is plus 1 over square root 2 plus 1/2 times z minus, plus, 1/2 z minus pi over 4. Did I get that right? No, I put the wrong numbers in. Let's try again. One more time, sorry about that. But you gotta put the components of the normal vector a, b, c are these. 1 over square root 2 is a, minus 1 over square root 2 is b, 1/2 is c, and then this multiplies x minus x0 is 1 over 2 square root 2. This multiplies y minus y0 is 1 over 2 square root 2. I'm sorry, this pen is so big it's hard to write. Plus 1/2 z minus z0 is z minus pi over 4. All equals 0. And there it is. There's an equation of the plane. You really want to probably multiply this through by 8 or something to get rid of the denominators and make it look a little simpler. But there's the equation of the tangent plane that you can get using these parametric surfaces. Well, I want to point out that the parametric surfaces also lend themselves to another formula for surface area. We said before that the little tangent plane over the top had area dr du cross dr dv. What that tells you is that another way to calculate the surface area is just to take the limit of the sum of dr du cross dr dv times the area of the plane region. This was the cross product of the two vectors' length. And you just have to take the limit of the sum of those as the number of pieces goes to infinity. It can also be written just as the double integral over r of the length of dr du cross dr dv dA by the definition of the double integral. So this is an alternate formula for calculating the surface area when a surface is given parametrically.